Good evening. Let's wait for some more time so that others will also join. So, is there any doubts regarding week 6 assignments that we have discussed? If there are no doubts, we can move on to today's session. I will share my slides now. Let's start with the summary of the week 7. By that time, let others can join. Is the slides visible?
Yes, ma'am.
Okay. So, welcome to week 7 assignment of NPTEL PMRF tutorials of Introductory Organic Chemistry II, August 2023 by Professor Harina Chakrapani and Professor Neeraja Deshaputre. Myself, Anisha Suresh, PMRF TA for this course from IIT Bombay. So, today we will be discussing about the summary of the lectures of week 7, followed by we will be solving the previous year assignment sets from 2022 and 21 August of Introductory Organic Chemistry 2. So, coming to the summary of week 7. So, in week 7, the following topics were discussed: conjugate addition, where we have discussed about 1 to addition and 1 for addition. Then, conjugate addition, kinetic versus thermodynamic products. Then, sir have discussed regarding hard and soft nucleophiles, followed by enol and enolate alkylation, then regioselectivity of alkylation reaction, followed by acylation of enol enolates and related name reactions. So, coming to conjugate addition, 1 to addition and 1 for addition. So, here you can see there is an alpha beta unsaturated ketone. It was treated with sodium cyanide in the presence of HCN at 5 to 10 degrees Celsius. So here 1 to addition of the Cn minus, which is a nucleophile, have taken place, giving the cyanohydrin. Here direct addition to the carbonyl have taken place. This is known as 1 to addition reaction. But in this case, when we raise the temperature to 80 degrees Celsius, conjugate addition have taken place, that is 1 for addition, giving this product. So you are clear why it is called 1 to addition and 1 for addition, right? Now coming to molecular orbital diagrams, which control the conjugate addition. So here the molecular orbital diagrams of butadiene and acrolein are given. So they are differing. just by the presence of an oxygen atom instead of this carbon atom in butadiene. Acrolein differs by the presence of this oxygen atom instead of carbon atom in butadiene. So here are the molecular orbital pictures of butadiene. First, the psi 1 orbital will be having all the lobes which will be similar. Then in case of psi 2, one second. So this is psi 1. Here there will be no nodes. All the orbitals will be of the same phase. When it comes to psi 2, here there will be a node. So these two will be similar and these two will be similar. There will be one node. And in case of psi 3, there will be two nodes. So here there will be a difference in the phase. These two will be of the same phase and there will be a difference in the phase here. And in case of psi 4, all the phases will be different. So we know that in case of butadiene, there are 4 pi electrons. So this will be 2, this will be 2. So it will be filling in the psi 1 and psi 2 orbitals. So psi 2 will be known as HOMO, which is the highest occupied molecular orbital. And psi 3 will be known as LUMO, which is known as the lowest unoccupied molecular orbital. Now coming to the molecular orbital picture of acrolein. In case of acrolein, since there is an electronegative oxygen atom that is present, the energy of the molecular orbitals will come down. So that is why it is shown like this. So compared to that of butadiene, the energy of the molecular orbitals of acrolein will be lower because of the presence of this electronegative oxygen atom. And because of the presence of this oxygen atom, there will be a difference in this difference in the distribution of this orbitals. So we can see that in case of psi 1, here the contribution of this orbital is lesser. In case of psi 2, the contribution of this orbital is lesser. In case of psi 3, we can see that this orbital have a greater contribution compared to others. And in case of psi 4, the contribution of this orbital will be lesser. So, similar to that of butadiene, here psi 2 will be the HOMO and psi 3 will be the LUMO. LUMO will be the lowest unoccupied molecular orbital, and it is this LUMO that will be reacting with the nucleophiles in case of conjugate addition. So we can see that psi 3 is having a greater contribution of this orbital, that is at this terminal carbon. So because of that, the nucleophiles that will be approaching, it can overlap with this orbital, and hence orbital interaction will be taking place, and it will result in the formation of a new bond here. So that is how conjugate addition is taking place. Because of the largest contribution of this N carbon, the orbitals of the approaching nucleophile will overlap with this orbital, and hence it will lead to formation of a new sigma bond here. So this is 1,4 addition that will be taking place. 1,4 addition or conjugate addition. Is the molecular orbital diagram clear? Any doubts?
Yes, it's clear.
Okay. Now coming to kinetic and thermodynamic control. Excuse me. So the kinetic product that will be formed is this 1,2 addition product. So this reaction will take place at a fast rate. However, it will be reversible. The cyanohydrin that will be formed here, when we mix it with organic solvent, it can give back this alpha beta unsaturated ketone. So this reaction will take place at a faster rate. However, it will be reversible. So this product is known as the kinetic product, which will be forming faster. However, it will be unstable, it will be reversible. But in case of conjugate addition product, the reaction will be taking place at a slower rate, but the reaction will be irreversible. So the product that will be formed, that is this conjugate addition product, will be more stable product. The reaction is slow, the reaction is irreversible, the product will be stabler product. This is known as thermodynamic product. This conjugate addition product is known as thermodynamic product. Now coming to the important points regarding the kinetic and thermodynamic control. So the product which will be forming faster, it is known as the kinetic product, and the product that will be more stable, it is known as the thermodynamic product. So we will be calling the conditions that will give rise to kinetic product as kinetic control, and the conditions that will give rise to thermodynamic product as the thermodynamic control. So is it clear what is kinetic and what is thermodynamic control is clear?
Yes, ma'am.
Okay. Now we have seen that attack can be possible either at this 1 2 position or at this 1 3 position. But greater electrostatic attraction will be more at this C double bond O, that is the carbonyl carbon. The electrostatic attraction will be more. So we will be having positive charge at this fourth position and the second position, but the electrostatic attraction at this position will be more. So reactions that are favored by electrostatics will give 1 2 addition product. Electrostatics will give rise to 1 2 addition product, and orbital interaction will give rise to 1 4 addition product. So we can see that in this both cases, a new CC bond is formed. A new bond is formed between this carbon and CN. In this case also, a new CC bond is formed. But in the first case, the CO pi bond is broken. The CO pi bond, which is having a energy of 369 kilojoule per mole, is broken. But in this case, ACC sigma bond, sorry, AC double bond C pi bond is broken, and the energy of the pi bond is only 280 kilojoule per mole. So here we are breaking a bond that is higher in energy and giving rise to a CC sigma bond. In this case also a CC sigma bond is broken. Um, Sorry, a CC sigma bond is formed, but we are breaking a C double bond C pi bond, which is having lower energy. So this product will be the more stable product when we compare the energetics. Now coming to the concept of hard and soft nucleophiles. The nucleophiles that will be smaller in size and higher in electron density, they are known as hard nucleophiles. Smaller size, larger electron density. If they are smaller in size, the electron density will be concentrated in very small portion. So because of that, they will be having larger electron density. Such nucleophiles are known as hard nucleophiles. Some examples are F minus, OH minus, OR minus, SO42 minus, Cl minus. Then coming to like neutral nucleophiles, water, ROH, ROR dash, RCOR dash, NH3, RMGBr, RLi. These all are examples of hard nucleophiles. And when we discuss about soft nucleophiles, they will be larger in size. The ions or the atoms will be larger in size. Because of that, the electron density will be diffused electron density. That means it will be spread over that entire molecule. So overall, if we are considering electron density, the electron density will be smaller in case of soft nucleophiles. So some examples of soft nucleophiles are I minus, RS minus, RSC minus S2 minus RSH, RSR dash, R3P, alkenes, aromatic rings, etc. are examples of some soft nucleophiles. So we can see the size of sulfur, iodine, selenium, phosphorus. These all are larger. So these are why they are known as soft nucleophiles. And some of the nucleophiles which have an intermediate nature between this hard nucleophiles and soft nucleophiles, they are this N3 minus, Cn minus, RNH2, RR dash NH, Br minus, etc. So this is clear. What is hard and soft nucleophiles?
Yes, ma'am.
Okay. So now we will be discussing regarding the reactivity of hard and soft nucleophiles. So the hard species reactions of these hard nucleophiles will be dominated by charges and electrostatic effects. So the hard nucleophiles, they will react in react where there is electrostatic effects or charges that will be dominating. In case of soft nucleophiles, their reactions will be dominated by this orbital effects. So soft nucleophiles will react based on orbital effects. Then hard nucleophiles will react with hard electrophiles. Soft nucleophiles will react with soft electrophiles. So hard, soft interaction will be there. Hard react with hard, soft react with soft. So, in case of hard nucleophiles, we have seen that hard nucleophiles, their reactions are dominated by charges and electrostatic effects. And in case of 1,2 addition, here this electrostatic effect is more dominating. So, hard nucleophiles, they will react at the carbonyl carbon of an enone. That is, 1,2 addition will take place if there is hard nucleophile. And in case of soft nucleophiles, they tend to react at the beta carbon, which is soft, of an enone and lead to conjugate addition. So we have seen that conjugate addition will be taking place in case where the orbital interaction will be favored. So soft nucleophiles will favor orbital interaction, hence they will undergo conjugate addition. And hard nucleophiles will give rise to 1,2 addition product. So this is all about hard and soft nucleophiles. So is this clear?
Yes, ma'am.
Okay. Now coming to alkylation reaction of enols or enolates. So the first step for alkylation reaction will be the formation of enolate anion. So if the base is strong, complete formation of anion will be taking place. If the base is strong base, the base can abstract this proton and give rise to this enolate completely. And if it is a weak base, there will be an equilibrium between the starting material and this enolate. So equilibrium will be favoring the starting material and small amount of enolate will be formed. Now the second step is alkylation reaction, that is an SN2 reaction with the alkyl halide. So this electron density of oxygen will be falling back and this carbon carbon double bond will break and it will attack on this carbon of this alkyl halide, and this halide ion will be leaving, giving rise to this product, alkylated product. So this is the general mechanism for alkylation of enols or enolates. And now coming to alkylation of aldehydes. So if we are having a base like LDA, so LDA can abstract this alpha proton of the aldehyde and give rise to this enolate, lithium enolate. So this deprotonation we are considering is taking place at minus 78 degrees Celsius. Now what will happen is that there will be still molecules of aldehyde, so it can undergo self condensation reaction. That is, the OLI bond will break, this CO double bond will form, and this bond will break, and it will go and attack on this electrophilic carbon of this aldehyde, and it will give rise to this aldol self condensation product. And other possibility is that even though this LDA is a non-nucleophilic base, there is in case of aldehyde, since it is very reactive, this can go and add on to this aldehyde electrophilic carbon as a nucleophile and give rise to this product. So it is better to avoid using lithium enolates in case of aldehydes. So what we will do for doing alkylation reaction of aldehydes, that is the next question. So for that, acylolates, they are the best general solution for alkylating aldehydes with most electrophiles. If the alkylating agents are SN2 reactives, sometimes enamines can also be used, and if the alkylating reagents are SN1 reactive, silylenol ethers can also be used. So we have discussed regarding this acylolates, enamines, silylenol ethers, etc. in the last week lectures. So in case of aldehyde alkylation, these three can be used as solution. So SN2 reactive alkylating agents we can use enamines, and SN1 reactive alkylating agents we can use silylenol ethers, and acylolates in general we can use for alkylating aldehydes. Now coming towards the regioselectivity of the reaction. So how regioselective formation of enolates will take place from ketone. So if we consider this ketone, so here there is alpha hydrogen present on this side as well as this side. So how we will get the desired product? So if this proton is subtracted, it will give rise to this enolate. So this enolate is more substituted enolate. So because of that, it can be known as thermodynamic enolate, because since it is more substituted, it will be more stable enolate. And if this proton is subtracted by the base, it will give rise to this enolate. This is less substituted, hence it will be less stable. So this is known as kinetic enolate. So, what are the general features of thermodynamic enolate? They are more substituted, more stable, favored by excess ketone, high temperature, and long reaction time. If the reaction time is more, it will give rise to the more stable product, and high temperature favored if there is excess ketone. And in present kinetic enolates, they are the less substituted enolates. They are less stable. They are favored by strong hindered base. Strong hindered base. Hindered base like LDA, which will be having bulky group present on them. So that is the strong hindered base. Then lower temperature, short reaction time. These will favor the formation of kinetic enolate. So these are the conditions that will give rise to thermodynamic enolates and kinetic enolates respectively. So are you clear what is thermodynamic and kinetic enolate? So is that clear to everyone?
Yes, ma'am.
Okay. Now coming to the acylation of the carbon, there are several name reactions that will be leading to, like similar to alkylation, acylation of this um, enolates etc. will be giving rise to several name reactions. One such reaction is this Claisen ester condensation. So in case of Claisen ester condensation, we will be having two ester molecules. So alpha proton of the ester will be abstracted by the base. We will be using base like NaOET etc. So OET minus will be abstracting the proton, alpha proton, giving rise to this enolate. So once this oxygen will be falling back, this carbon-carbon double bond will go and attack on this carbonyl carbon, which is electrophilic, and it will give rise to this intermediate. So all these reactions are reversible. Then once this oxygen will come back, this OET, which is a better living group, will be eliminated, giving rise to this product. Still, you can see this reaction is reversible. So, how this reaction will become irreversible? For that, again there will be base present in the system and there will be alpha proton. So that alpha proton will be abstracted, giving rise again the stable delocalized enolate. Then if we do the final workup, so this will come back and it will abstract proton from the water. We are working up with HCl and water, so it will give rise to H3O plus, and this enolate can abstract proton, it will give rise to this product. So now since this proton is abstracted, this step have become irreversible, and the product that we get finally will be in good ratio, and this will be irreversible reaction now. So this is Claisen ester condensation. Another name reaction is Stobbe condensation. So in Stobbe condensation, we will be having a diester like this. So in the presence of base, that diester proton, alpha proton will be abstracted, and we will get this anion. So that anion can go and add on to this electrophilic carbon of this ketone, and we will get this intermediate. Now this tetrahedral intermediate, this O minus can go and add on to this carbonyl carbon of this ester, because it will lead to formation of a 5-membered intermediate. So it will lead to formation of this tetrahedral intermediate, and once this will fall back, this OET will be removed. OET will be a better leaving group, giving rise to this. So this is known as lactone. Cyclic esters are known as lactones. Now what will happen? Again base will be there, like OET or something will be there present in the medium. It can abstract this proton and it will open up. So now we will be having a CO2 minus and OET. So this reaction is known as Stobbe condensation. Now if we do workup, it will give rise to R, R double bond, CO2H, CO2 ET. So this reaction is known as Stobbe condensation reaction. Condensation reaction, since there is removal of some moiety. So here the OET, ethanol is removed. Because of that it is known as condensation. So is these two reactions clear?
Yes, ma'am.
Okay. Now coming to Noven angle condensation. In case of that, we will be having an alkene. We will be having an alkane. So the base can abstract this proton. So here some electron withdrawing groups can be present. So the base, here this nitrogen base will be abstracting this proton, giving rise to this anion. This anion will be adding on to this carbonyl carbon of the aldehyde, giving rise to this tetrahedral intermediate. So nucleophilic addition reaction is taking place here, and the medium will be having H plus ions, which will be abstracted by the base. So it can form OH here, and again base will be abstracting. This base can abstract this proton. So even CB reaction will be taking place, dehydration will be taking place, and it will give rise to this alkene. So since water is removed, this is known as condensation reaction. So here one molecule of water is removed. Because of that it is known as condensation reaction. This is Noven angle condensation. Now coming to Darsen's glycidic ester synthesis. So here we will be having a alpha halo ester. So the base will be abstracting the proton alpha to the ester, and we will be getting an enolate like this. Now what will happen? This O minus will come back, and this anion that will be formed here, it will go and attack on this ketone, and this CO double bond will be breaking. Now what will happen? O minus will be here. A tetrahedral intermediate will be formed. This O minus can attack the Cl in SN2 fashion, and it will be removed. This carbon in SN2 fashion, and the Cl, which is halide, which is a better leaving group, it will be removed, and we will get this epoxide. So Darsen's glycidic ester synthesis, it will give rise to epoxide. So we are having alpha halo ester. From that, it will give rise to epoxide. So this is another important reaction from this enolate acylation reaction. Now, other several reactions which we will be discussing while we are solving problems will be Diekman reaction, Robinson annulation, Henry reaction, Stokes-Enamine reaction, etc. So these are also discussed. The mechanism of these reactions are discussed briefly in week 7. Now, for references, you can follow Claydon Organic Chemistry, Chapter 10 for conjugate addition, Chapter 26 for alkylation of enolates, Chapter 28 for acylation at carbon for enolate, and this for conjugate addition reactions of enolates, Chapter 29. So, the summary of week 7 is clear for everyone. Is there any doubts regarding any of the topics that we have covered?
Yes, ma'am. It is clear.
Okay. Now coming to question number 1 of this week 7 assignments. The first question is identify the intermediate X and the final product Y in the given reaction sequence. So we are having an alpha beta unsaturated cyclohexenone. So we are treating it with LD at minus 78 degrees Celsius followed by methyl iodide and finally quenching with water. So it will give rise to some product X. That product X is treated with thiophenol in presence of triethylamine that will give rise to Y. So we are asked to identify X and Y from the given options. Any answers?
Fourth option.
Fourth option will be the right option. We can see the mechanism. So here we are having this alpha beta unsaturated cyclohexenone. So in presence of LDA, what will happen? LDA will be abstracting this alpha proton. It will give rise to this lithium enolate. Now this lithium enolate, it will, this oxygen lone pairs will fall down. This carbon carbon double bond will go and attack on this me carbon of this methyl iodide, and this iodide will be leaving, giving rise to this compound. So alpha methylation will be taking place here, and upon treating with water we will get this compound X. So X will be alpha methylated cyclohexenone. Now we have PSHS, PHSH and triethylamine. So triethylamine will be abstracting the proton from PHSH, giving rise to PHS minus. So this is a soft nucleophile. We have seen when we were discussing hard and soft nucleophile, PHS minus will be a soft nucleophile. So it will undergo 1,4 addition reaction. So PHS minus, it will attack here. It will give rise to this enolate. And once this is falling back, it can abstract the proton that will be abstracted by the base, giving rise to this compound Y. Is the mechanism clear?
Yes, ma'am.
Yes, ma'am.
Okay. So the right option will be option 4 for question number 1. Now coming to question number 2. The scheme below outlines a mechanism for the synthesis of a ketone hex 5-ene 2-on from ethyl 3-oxobutanoate and acetoacetic ester ketone synthesis. In which stage do the curly arrows wrongly show the flow of electrons? Predict the structure of the enolate formed in the given reaction. So here we have to find which curly arrows represent the wrong flow of electrons. So first this OET minus, which is the base, will be abstracting the proton, giving rise to enolate. And this oxygen will be falling back, and this double bond will be go and attacking on this allyl chloride, giving rise to this product. And which upon hydrolysis, this ester will be converting into acid. Then we have seen that if there is high temperature, then this sort of reaction can take place where CO2 will be removed, right? Then this tautomerism is shown here. 4 to this is tautomerism. So at which stage the arrows shown are wrong?
Totalitarianism is wrong.
Yeah, tautomerism stage the arrows shown are wrong. Actually the arrows will be like this. This will go and attack on this proton and OH minus will be removed, giving rise to this ketone. Clear? Any doubts? So the right option will be stage 4. Anyone having any doubts?
Clear, ma'am.
Okay. Now moving to question number 3. Here, which is the main product of the following reaction? So a diester compound is given. It is treated with NaOET in presence of ethanol and quenched with water in presence of HCl or something. So what will be the product that will be formed here? So this will be a name reaction that is known as Beekman condensation, which is similar to intramolecular Claisen condensation reaction. So what will be the main product that is formed here?
Cyclopentane.
Five-member ring.
Which option?
The option is
Option 2.
second option.
Option 2. Option 2 will be the right answer. We can see the mechanism. So here OET minus from NaOET will be abstracting one of the alpha proton. So it will give rise to enolate. And when this is falling back, this carbon-carbon double bond will go and attack on this carbonyl carbon of the other ester, giving rise to this tetrahedral intermediate. And once this is coming back, this O minus will be falling back, OET minus will be leaving. It will give rise to this product. And for making the reaction irreversible, there will be a alpha proton here that will be abstracted again by the base. Then it will give rise to this enolate. And once if we are working up with water, when we are working it up with water, it will give rise to this product in very good yields. Is the mechanism clear? This is known as Beekman condensation reaction. Is this clear?
Yes, ma'am.
Okay. So the right option will be option B, which is this 5-membered product. Now coming to question number 4. The major product formed in this following reaction is, so here we have a active methylene group and a conjugated alpha beta unsaturated ketone. So we are treating it with MEONA, NaOMe in presence of methanol. So what will be the product that will be formed?
Last option.
Last option will be the right option. We will see the mechanism. So here we are having this active methylene group. We have seen that in case of active methylene group, the central hydrogen will be more acidic because of the presence of these two carbonyl groups. So the base will be abstracting that proton, giving rise to this enolate. And once this oxygen will be falling back, this CC bond will go and attack on this 1,4 position. So this is known as Michael addition reaction. 1,4 addition reaction is also known as Michael addition. So it will go and attack at this 1,4 position. Then this will shift in this fashion and O minus will be formed and another enolate will be formed. And once this will be falling back, it will get protonated, giving rise to this product. So is the mechanism clear?
Yes, ma'am.
So the right option will be option 4. Now coming to question number 5. So I think this question was already discussed in one of the previous lectures. So what is the final product of the given reaction occurring via the silyl enol ether intermediate? So in presence of triethyl amine and TMS chloride, this proton will be abstracted by this triethyl amine, giving rise to this intermediate. So this O minus which will be formed will attack on TMS chloride and the Cl minus will be leaving, giving rise to this. And it is treated with TiCl4 and benzaldehyde. So what will be the product that will be formed here?
First one.
First one. Right option will be option number B. We will see the mechanism, then it will be clear. So in here, this is a general mechanism. So our substrate is like this: OSIMe3 double bond. So here, this is our intermediate. So it is treated with TiCl4 and benzaldehyde. So what will happen? TiCl4 will coordinate with the benzaldehyde, making this carbon more electrophilic. Now this lone pair of oxygen will fall down, and this carbon-carbon double bond will go and attack on this electrophilic carbon, and this will push this electron density so as to neutralize this positive charge. So we will get this intermediate. Now the Cl minus that will be removed from this TiCl4, it will abstract this silicon SiMe3. It will be having affinity towards silicon. It will abstract this, and this bond will break and it will neutralize this positive charge here. Now another chlorine molecule will add on to this TiCl3, giving TiCl4 back, and this bond will be breaking. It will go and attack on this Me3SiCl. So Cl minus will be leaving and we will get this product. So in our case, we are having R, we are having CH3 in place of R. So here there will be CH3 and here there is one more CH3 present. So here there will be one more CH3 present, and this upon hydrolysis it will give rise to CH3 double bond OH, pH. So option B will be the right option. Clear? You can see the mechanism again.
Yes, ma'am.
So this is our starting substrate. So here they are showing R, R double bond O CH3 was a substrate that is shown here. In our case, this is the starting substrate. So it will give rise to this product. Clear? So this reaction will take place only if we will be adding TiCl4. Lewis acid is needed to get silylenol ethers to react. The key step is an aldol attack of the silylenol ether with the Lewis acid complex electrophile. So if we have to use this TiCl4 must in case of this reaction. And this is also a name reaction which is known as Mukayama aldol condensation. Mukayama aldol condensation reaction. So it is not necessary that you memorize all the names of these name reactions, but you should be clear about the mechanism and what will be the product. What will be the um, how this reactants will be reacting to give rise to the product. That should be clear. Even if you forget the names, it is okay, but the mechanism and the product should be clear to you. Okay. So the right option here will be option B. Any doubts?
No, ma'am.
Okay. Now coming to question number 6. Which of A to D is the intermediate compound A in the following reaction? So, out of this four, what is the compound A that will be formed in this reaction? So, something is formed here after reaction of these two substrate. So, it will give rise to some intermediate A, and this can be converted in two steps to this compound. So, what is that compound?
Option B.
Option B will be the right option. We will see the mechanism. This is known as Robinson annulation reaction. So first what will be happening is, here there will be a proton, right? Since it is between this two carbonyl groups, it will be the most acidic proton. It will give rise to an enolate. So here we are using NaOH. So NaOH will be the base. So it will abstract this most acidic proton, give rise to enolate, and this enolate, once it is coming back, it will give rise to this conjugate addition product. And we are having one more enolizable group here. So it will undergo intramolecular aldol reaction to give rise to this product. So stepwise you can see, first this enolate will be formed because this is the most acidic proton here. So this enolate, this O minus will be coming back. This carbon-carbon double bond will go and attack at this 1,4 position, and it will give rise to this intermediate. Now this can abstract proton from the medium, giving rise to this conjugate addition product. Now what will happen? Now the next step will be intramolecular aldol reaction. So for that to happen, we are having an enolizable hydrogen here. The base will be abstracting. In our case, OH minus will be abstracting this hydrogen, and it will give rise to this enolate. Now this will be, this O minus will be coming back. This carbon-carbon bond will go and attack on this uh, carbonyl carbon, giving rise to this tetrahedral intermediate, and proton will be there in the system. So upon protonation, it will give this aldol product. Now this final step is E1CB dehydration or the condensation reaction. So for that, again base will be present, enolate will be forming, and once it is coming back, this OH minus will be removed, giving rise to this alpha beta unsaturated ketone. So this reaction which is taking place here, this is known as E1CB reaction, and it will give the final product. Is the mechanism clear? This is a name reaction known as Robinson annulation reaction. Any doubts in the mechanism?
No doubt.
Okay. So option B is the right answer. Now coming to question number 7. What will be the product of the following reaction? A nitroalkane and a ketone or aldehyde is given in the presence of a base or solvent. It will give rise to some product. So what will be that product? It is alpha nitroalcohol, nitroalkene, beta nitroalcohol, beta amino alcohol. What will be the product?
Beta nitroalcohol.
Beta nitroalcohol will be the right option. This is Henry reaction, which is also another example of enolate acylation reaction. So here, since nitro is an electron withdrawing group, this hydrogen will be acidic hydrogen. Now what will happen? The base will be abstracting that acidic hydrogen, giving rise to this enolate. Here, this will be similar to the enolate. So this anion will be there. So once it is falling back, this carbon nitrogen bond will go and attack on this carbonyl carbon, giving rise to this tetrahedral intermediate. It can undergo protonation to give rise this beta nitro alcohol. So this is the alpha position, this is the beta position. So this is beta nitro alcohol. Clear? This is known as Henry reaction. Any doubts?
No.
Okay. So beta nitroalcohol is the right option. Now coming to question number 8. Which of the following is not true about enamines? So four statements are given, out of which is the wrong statement. Enamine are derived by the condensation of an aldehyde or ketone with a primary amine. Enamines are versatile intermediates. Enamines are considered to be nitrogen analogues of enols. They are tautomeric form of imine. So which is the wrong option?
Second one,
Hmm?
they are not versatile intermediate.
Enamines are one of the versatile intermediates, right? Similar to that of enolates. Enamines can also undergo, like, it will form intermediates and it will give rise to, in case of aldehydes and all, for alkylation reaction they will be versatile intermediates, enamines, in case of aldehydes and all. Right option will be option A, because they are formed by the condensation of aldehyde or ketone with a secondary amine, not a primary amine. So we will see the enamine formation reaction. So we will be having an aldehyde or a ketone. So it will react with a secondary amine to give rise to this enamine. So the mechanism is clear. Like, it will add on here, OH it will form. Again, it will add, it will form R double bond NRR plus CH3. Then this one of the proton will be removed, and it will give rise to. So this is how an enamine is formed. Then this is an example of enamine conjugate addition reaction. So this is known as Stoke-enamine reaction. Stoke-enamine reaction. So we are having a secondary amine here. So it will give rise to enamine. So now the lone pair on nitrogen will fall down. This carbon-carbon bond will break. It will attack at 1,4 position of this alpha beta unsaturated ketone, giving rise to this intermediate. Now what will happen? This will abstract proton from the medium, giving rise to this ketone, and another molecule of enamine can, another enamine will be forming here. And if we do hydrolysis, this enamine will be converted into carbonate. So this reaction is known as Stoke-enamine reaction. So is this clear? Why the first option is not true? Because enamines are derived by the condensation of aldehyde or ketone with a secondary amine. Imines can form if there is primary amine as well, but enamines will not form. Okay.
Yes, ma'am.
So this is the right answer. Now coming to question number 9. Which of the following reaction does not indicate the correct main product? So four different reactions and their products are given. So out of which one of the product that is given is not right. So you have to identify that. So which of the following reactions does not indicate the correct main product?
Third option.
Yeah. Option third is the reaction where the product that is formed is not the right one. So we will see the each of the mechanism of these reactions. So coming to the first reaction, here we are having this ketone. So we are having this Me2NH, which is a secondary amine. So it will give rise to enamine. So that is right. It will give rise to enamine. This is tautomerism. Now, the second reaction is we are having an enamine, and this lone pair on nitrogen will be coming. This will go and attack on this carbon. This bromide will be leaving, and it will give rise to this product, and which upon treating with or hydrolysis, it will give rise to this ketone. So this is also correct. So these two are correct options as given. Now coming to the third one. So we are having triethylamine. It will give rise to this enolate, and this O minus will go and attack on this SiMe3, silicon of this SiMe3. Chloride will be leaving, and it will give rise to this product. But what they have given is this product. So this is a wrong option. That is, the product that is formed here is not right. So the correct option will be this one. Now we will see the final one. So here we are having this chloride and TiCl4. So this Cl will coordinate with TiCl4 and it will get removed as TiCl5 minus. So here a carbocation will be generated. Now Cl minus that will be removed. It can abstract SiMe3, and this will lead to formation of an enolate. So this O minus will fall down, and this will go and attack on this like a carbocation that is formed here, and it will give rise to this product plus Me3SiCl. So the option that is given here is right option. So the wrong product was given in option number 3. So is it clear? This is not the right product. The right product that will be formed here will be OSIMe3 double bond. All other options are correct options. The only uh, the only reaction in which the wrong product is marked is option 3. So according to our question, the right option will be option 3. Clear?
Yes,
Okay.
ma'am.
Now coming to question number 10. So which of the following reaction show a correct main product? So different reactions and their products are given. They are asking which of this reaction is shown the correct product. In which of these reactions is shown the correct product.
Second reaction is correct.
Second one will not be correct because here this LiNme2, it is a bulky base. So it will not give rise to a thermodynamic product. We have seen when we were discussing thermodynamic and kinetic enolate that bulky bases will give rise to kinetic enolate. So the right option here, the right answer here will be OLi like this. Because this is a bulky kind of base. Bulky bases give rise to kinetic products. And you can see the temperature, it is lower temperature. At lower temperature, the reactions that will be taking place faster will only occur.
Third option.
Third option will be the right option because this KH here H minus will be um, a smaller and a smaller base, so it can abstract this proton easily and it can give rise to this product. Now we will see the mechanism for each of these reactions. So first reaction, which is Claisen ester condensation. So here this O minus will be abstracted. OET minus will abstract this proton, giving rise to this enolate. Once this will come back, this carbon-carbon double bond will go and attack on this carbonyl carbon, giving rise to this tetrahedral intermediate. Now once this O minus will be falling back, this OET minus will be removed, giving rise to this product. So these all are reversible steps. Now for making this reaction irreversible, again this proton will be abstracted and one enolate will be formed, and once it is coming back, upon workup H plus ions will be abstracted and this will be formed. So this is the product that will be formed in this reaction, but they have shown a different product, right? So there is no CH3 here. Instead, they have mentioned CH2 here. So that is wrong option. Here only CH3 is there. Now in the second case, LiNme2, it will be abstracting this proton that will be present on the less hindered side. It will give rise to this enolate, lithium enolate. So they were given in the option enolate will be formed in the side. So that is wrong. So this is the correct product that will be formed here. And in case of KH, it will be abstracting this H minus will be it will be K plus and H minus. H minus will be abstracting the proton. So this is smaller base. It can abstract this proton easily, giving rise to this thermodynamic enolate. Now this reaction PHBr, here SN2 reaction will not be possible. So it will not give rise to the product that was mentioned here. And since A lithium halogen exchange can take place. This can give rise to PHLi, and this upon hydrolysis it will give benzene. So this product that was mentioned in the question, it will not take place because SN2 reaction is not possible in case of this reagent. Clear? Any doubts?
No, ma'am.
Okay. So the right option will be option 3. Now coming to question number 11. Which ester will not give a good yield of the Claisen condensation product with NaOET in ethanol? So different esters are given which will not give rise to good yield of Claisen condensation product.
Fourth option.
Fourth option. The right option will be third option. We will see why. Because this is a mechanism for Claisen condensation reaction. So the proton will be abstracted. It will give rise to this enolate. This will come back. It will attack on this carbonyl carbon, give rise to this tetrahedral intermediate. And once it will collapse, this OET minus will be removed. So all these steps are reversible steps. For the reaction to be irreversible and give a good yield, this proton again will be abstracted, and upon hydrolysis it will give the beta keto ester. So this alpha hydrogen, the presence of this alpha hydrogen is important for giving better yield of this product. So, if the original ester has two substituents on the alpha carbon atom, the formation of the stable enolate of the product is no longer possible as there are no hydrogen atoms left to remove. So, in our case, we are having two methyl groups here. So, giving rise to this product, here you can see the equilibrium is favoring the not favoring the formation of the desired product. It is giving back the starting material mostly. If there will be any hydrogens present, it can be abstracted and it will lead to formation of this Claisen condensation product. Since there are no hydrogens left, this reaction will give only lesser yield of the product. Clear? So in this case, here there is two more alpha hydrogens that will be present. Here also alpha hydrogens will be present. But in this case, there will be no alpha hydrogens present after Claisen condensation. So because of that, like the reaction will not be ir- uh, the reaction will be reversible. It cannot be made irreversible, and hence the yield of the product, Claisen condensation product from the substrate, will be lesser. Is it clear? Hello.
Yes, ma'am.
Okay, so the right option will be option number 3. Now coming to question number 12. What would be the starting materials used if the following molecule was made using a Robinson annulation? So this is the product that is formed. So they are asking what will be the starting materials that will be used in this case.
Option 4.
Option 4 will be the right option. We will see the mechanism. So we are having this 1,3 dicarbonyl compound. So the base will be abstracting the proton that will be present here. That sorry, not here. The base will be abstracting this proton, giving rise to this enolate. Now what will happen? This will be falling back. This will undergo 1,4 addition. It will give rise to this enolate, as we can see here. Now once it will fold back, this will go and attack on this carbonyl carbon. Sorry. Sorry. Now it will abstract the proton and give rise to this give rise to this conjugate addition product. Now what will happen? Again, this enolizable hydrogen is present here. This enolizable hydrogen will be abstracted by the base, giving rise to this enolate. Now what will happen? This enolate will fall down and this will go and attack on this carbonyl carbon, giving rise to this aldol product. This will undergo protonation and it will give this aldol product. Now it will undergo E1CB dehydration reaction. That is, this proton will be abstracted, this enolate will be formed, and once it will be falling back, this OH minus will be leaving, giving rise to this E1CB product. So this was a product that was given to us. So the starting materials that will be used is this ketoester and this alpha beta unsaturated ketone. Now the other options, here this diketone is given, it will give rise to this product. You can work out the mechanism yourself. And here this ketone, it can undergo Robinson annulation, giving rise to this product. And this will undergo intramolecular Robinson annulation reaction, giving rise to this product. This mechanism you can work out yourselves and see if you are able to write the mechanism properly. So the right option here will be, the starting materials is option A, option D, where this product is formed from these two starting materials. Here, any doubts?
Yes, ma'am.
Okay. Now coming to question number 13. What is the major product that will be formed in the following transformation? So here we are treating this alpha beta unsaturated compound with methyl magnesium chloride in presence of copper chloride and then quenching it using allyl chloride. So what will be the major product that will be formed in this transformation?
Option 4.
Option 4 will be the right option. It is similar to that of the first reaction, similar to, most similar to that of the first reaction that we have discussed. So we are having this alpha beta unsaturated ketone and we are treating it with MeMgCl and copper chloride. So it will give rise to MeCu, which is Gilman's reagent. It will favor 1,4 addition reaction. So 1,4 addition of methyl will be taking place. Here methyl minus 1,4 addition will be taking place and this enolate will be formed. Now what will happen once it is falling back? It will go and attack on this allyl chloride, removing the Cl minus, giving rise to this product. So this allyl will be coming in the plane opposite to that of the phenyl, so as to reduce the steric hindrance. Clear?
Yes.
Okay. So the right option will be option 4. Now coming to question number 14. Which of the following is the product of the given reaction sequence? So here this compound is given, it is treated with H plus and heat. So here aldol condensation reaction will be taking place. So what is the product that will be formed here? Major product that will be formed in this reaction.
Second option.
First option.
First option will be the right option. We will see the mechanism, then it will be clear. So we are having this compound in hand. So we are having H plus medium. So acid catalyzed aldol condensation will be taking place. So this enol will be forming, and this enol will be forming. This will be protonated. So this enol will be forming, and this can undergo this mechanism, like this oxygen lone pair will fall down, this carbon carbon double bond will go and attack on this carbonyl carbon. So it can attack on either side, both will be similar, and a tetrahedral intermediate will be formed. So here first O minus will be formed, and it will undergo protonation to give rise to this aldol product. Now what will happen again, like protonation can be taken place, then this will give rise to another enol, and this OH will again protonate to give OH2 plus, and this will undergo E1CB removing water to give rise to this product. Clear? Any doubts?
Clear, ma'am.
Okay. Now coming, so the correct option in this question is option 1. Now coming to question number 15. When aldehydes lacking alpha hydrogen is treated with concentrated solution of a strong base, Cannizzaro reaction take place. The plausible mechanism of the reaction is given below. So we have seen Cannizzaro reaction in last week. So if aldehydes are not having any alpha hydrogen, then the hydroxide will undergo direct addition to the aldehyde. It will give rise to alcohol and carboxylic acid products directly. A disproportionation kind of reaction will be taking place there. So here the OH will be adding here, and it will give rise to this tetrahedral intermediate. This reaction is faster in rate than this intermediate. Here, once it is falling back, this hydrate will add on to other molecule of the aldehyde. So this hydrate transfer is the slowest step in this reaction. So it will give rise to, from here a carboxylic acid will be formed, and this will give rise to alcohol upon abstraction of this proton. So this is also fastest step. So we know that for determining the rate of the reaction, we will be considering the slower step, that is the rate determining step. So what will be the rate law derived from the above mechanism?
First option.
Hmm? Which option?
Option 1. First option.
Option 1. But we are having two molecules of ARCHO, because this is not the step, this is the step. So we will consider a sum of these two steps, like AR double bond OH plus OH minus plus AR double bond OH. It is giving rise to this slower step, because this intermediate, this is formed from these two starting materials. They have not mentioned any intermediates here. So the rate determining step will be considering these starting materials. So the intermediate that is formed will be from these two starting materials, and the intermediate again will be reacting with other molecule of the aldehyde, giving rise to the products. So they have mentioned this is the slowest step, which will be the rate determining step. So R equal to K into concentration of the starting materials. So ArCHO, two molecules of ArCHO will be there. So because of that, we will mention the coefficient in power, and OH minus will be there. That will be 1. So the right option will be option number 3. So for finding the rate of the reaction, a rate law shows how the rate of the chemical reaction depend on the reactant concentration. For a reaction such as AA give products, the rate law generally has the form rate equal to K into concentration of A, that is reactants, to the power N, where K is the proportionality constant called the rate constant, and N is the order of the reaction with respect to that of A. The value of N is not related to the reaction stoichiometry and must be determined by the experiment. So this cannot be determined by the stoichiometry of the reaction, that is how much number of molecule, it will be determined by that of the experiment. So for a reaction given by AA plus BB gives CC plus DD, where A, B, C and D are the stoichiometric coefficients of the reactants of products, the rate equation for the reaction is given by rate equal to concentration of A to the power X and concentration of B to the power Y. So rate, this is the proportionality, this is showing rate is proportional to that of the concentration of A to the power X and B to the power Y. So we can introduce a proportionality constant K and write rate equal to K into concentration of A to the power X and B to the power Y. So we in our case we have seen the mechanism, and from that we are introducing these coefficients. So A and B denote the concentration of reactants A and B. X and Y denote the partial reaction orders for A and B, which may or may not be equal to the stoichiometric coefficients. Then proportionality constant K is the rate constant of the reaction. So this is how we will be finding the rate of a reaction. In our case, we can see that this is the rate determining step, and these are the reactants. So here they are not considering, like they are not considering this intermediate as a reactant itself. Instead they are considering it as a product formed from this two reactants. So we can write this intermediate as ArCHO plus O minus. So these are the three reactants. So these three reactants will give rise to this products. So this is the rate determining step. So hence we can write this as the rate equation. Is that clear?
Yes, ma'am.
Okay. So this was the last question in this week. So is there any doubts regarding any of the questions that we have discussed today? If there are no doubts, we can wind up today's session. Thank you everyone for joining in today's session, for dedicating your time to listen to this lecture.
While our sports shall be
Thank you, ma'am.
seen on the
Thank you.
echoing green. Thank you, ma'am.